you. So I talk about the inflow similarity within urban of the sublayer. So now we are concerned about flow characteristics solely dependent on the boundary building geometry. The past study have shown such characteristics. Product chain Castro conducted internal experiment over cubical homogeneous cubical hierarchy and finds the constant roughness sublayer height independent of roughness boundary height. So it's because it's a problem solving they depend on the building geometry. Kristen and Rhodes have also shown the identical power shapes for the corresponding wind directions. So for the real city and also the other the field model experiment. So we further evaluate the similarity for the case of 3D distribution in complex realistic urban geometries and also for under different inflow conditions. So the objective is this, and we conducted numerical simulation and evaluate the similarity for the three-dimensional values under different inflow conditions, and also neutrality between the summer condition situation and the it is something like a windy condition like in the typhoon case. And also we also introduce some applications of the such as similarity characteristics. So I explain more detail about what we are thinking about meaningful similarity about roughness sublayer. So similarity assumption says the non-dimensional velocities is expressed by the universal function. In case of inertial sublayer, as we side, it is just dependent on the height and the building geometry. And we know that the equation that such a universal functions is expressed by the logarithmic function equation. And in case of roughness sublayer, we also assume that it is non-linear velocity just follows the universal function, but it's not necessarily depend on the height, but it is three-dimensional variation. So now it's dependent on x, y, and z, and also the building geometry. Main difference is that the empirical universal function is maybe will be impossible to obtain analytically, nor even such a simple equation form would be very difficult to obtain. But still, it is possible to get the numerical solution. So we confirm it using Ratz-Rhodes migration model. I don't explain detail about the model, but so we check the literature in the bottom right. And just write this key point. So the momentum equation follows the Boltzmann equation, but not the Navier-Stokes equation. Although they are mathematically equivalent. And why we use this model is because this equation model is very suitable for the coding for the GPU computation. And our institute have a massive GPU cluster, so therefore we have to use it. So this is the simulation settings. So we target is the Shinjuku area. This is the part of Tokyo, and the full size is 6.4 kilometer by 6.4 kilometer. Then it's connected to the driver regions of the same site in the wind side. So we conducted three different simulations. It's changing the configuration of the driver region. KSMD has no building, so no driver region. So the lambda convenience flow is incoming to the target region. KSHH is the second. It's our homogeneous, it's regularly cubes, whose height is the same as the average building height in the target region. And to the case H4H, also same horizontal arrangement of the case HH, but there are two different size of buildings, 8 and 4 times of the smaller. So these three simulation cases will reproduce the different inflow condition, different target intensity and the different boundary height. And the grid size is all 2 meters grid spacing, and simulation time is 5 hours, and the last 3 hours is for the grading. So this is the result. So boundary height is now complete on the x direction. So the index to the target region. The boundary height in the case H4H is around 300 meters, and the HH is around 200 meters. SMP has no boundary, so it's 0 meter. So boundary height is so defined, and also the turbulent intensity also very different. So now first we check the roughness sublayer height. It is a bit difficult to obtain in a realistic, very heterogeneous building geometry, but we try to estimate it from using the diagnostic plot. So, so and this is the plot is composed of the local turbulent intensity and the mean streamline mean wind velocity divided by Houston velocity. So this is the same meaning as the height. So the past studies after 2013, for example, have shown that the values in the logarithmic layer is all plotted on this line, red line. And it is separated in a roughness sublayer because roughness sublayer has more turbulent intensity and the lower remaining speed. So this separation point should be in the top of the roughness sublayer. So this is the result, and it's plotted in our also X. And for three defined simulations, the blue dot is the roughness sublayer height, and the yellow is the inertial sublayer is estimated by assuming the constant stress. So now the inertial sublayer height is very different among three simulation cases in the target region because the boundary height is dependent on the boundary height. But roughness sublayer height is almost consistent among three simulation cases. It's because of dependent on the just determined by the building geometry. Next, this is a grid to comparison of the streamlines velocity. And now it is compared that circle horizontal slice from 30 kilometers from the ground. So the grid total grid number in one slice is 10 million grids. So the main velocity, streamline mean velocity at each grid point and directly compared among the single simulation cases. So now the total domain is separated in X direction, five subsection. This is the inlet and this is the outlet. And this is the vertical axis, SND, H4H, and horizontal axis is HH. So generally, so they have almost a linear relationship, not bad correlation. But the slope is not one by one, not followed one by one line. So next I calculate this regression parameters, linear regression parameters, the correlation coefficient and the slope. So they are calculated each every height of the 640 meter by 640 meter. It increases 100,000 grids. And the top two panels are the correlation, bottom is the slope, and the left is the comparison of HH and ND, and the right is HH and H4H. First, let's see the correlation. It's worse in the inlet because, of course, it is in the defined from conditions coming from the left. So it's correlation becomes worse. But after 1 kilometer, 1 kilometer in the X direction, they are also nearly the unit. So it means that the flow is mostly fully adjusted to the surface condition. And also we can also see the correlation along X direction and these two lines. So this is also very clear if we see the streamline velocity at up to 6.4 meters. This is in the inertial sublayer. We can find the tall building here and behind, yeah, wake targets, maybe those wake targets are dominated and used by the wake targets. Clearly. But this signature is totally disappeared in case H4H. It's because the strong turbulent inflow may be more efficiently disperse the signature of the wake targets. Then correlation becomes worse. So next this is slope. Slope is gradually reduced to unity with increasing X. Now I consider about the meaning of slope. If similarity assumption is valid, then we can show this equation and it's modified to yeah, to this equation. Now slope is equal to the ratio of the velocity scale. Then based on this equation, we evaluate the candidate of the velocity scaling parameters. Firstly, this is the boundary layer height ratio. It's negatively correlated but not equal. But the U star ratio, this is calculated every 614 meters squares. It's almost equal to the slope. So it means that U star is still a very useful parameter to scale. Not only the special average variable, but also the local velocity component. So now if the velocity similarity is very robust, then it will be very useful to prepare the roughness sublayer mean flow database, something for defined mean directions. So for example, so if we can get from the regional representative used and mean direction from, for example, observation and the simulation, then we check, choose the corresponding mean direction and scaling by user. This is the animation. Um, Thank you. Yes, thank you. So if we update this input variable, then we can assess how the mean distribution becomes the rapid suffering. Then now we are also preparing the database for the case of Tokyo. It is 30 kilometers by 30 kilometers. We can still just mention this part. But not only mean speed, but also decay and other any statistics. Similarly, we can prepare. And this we use for the environmental assessment. Okay, thank you.
Any questions?
I like the idea of like using the sigma u, the second order statistics, to distinguish the roughness sublayer and the inertial sublayer. But that graph makes me wonder about the self correlation because I think you have the mean velocity on both axis and y-axis. So my question is, why uh, you could use the Townsend-Perry relation in the inertial sublayer where this sigma u over the mean velocity will follow kind of the logarithmic profile. And then the deviation from that logarithmic profile in the inertial sublayer can tell you the roughness sublayer height without suffering this self-correlation. That's
Right.
just my quick thought on that.
Yes. So
What do you think?
yes, thank you. So sometimes, in my impression, sometimes the logarithmic profile just seeing the velocity, mean velocity, within the roughness subray. Also, it's not gradually separated from the logarithmic profile. So the boundaries of the especially in a very height variation, the complex case, then we cannot find clearly the top of the roughness sublayer in, from the mean velocity distribution.
Yeah. That's why I said
So
I like,
therefore,
I like to
therefore,
use
yeah,
sigma u. Sigma
yeah,
u is better. I
yes,
agree on this one.
yes. And also there's not only this case, but the literature for the cast of 2013 also very carefully checked the reproduction, the profile, the fitting of to the universal line.
Yeah.
So not only experimental but also theoretically. So we can really rely on this diagram, I think.
One more question?
Uh, My question was regarding the inflow turbulence, like this driver region. So based on these results, like let's say we are doing a simulation for a realistic urban area and we need some inflow turbulence. So do you recommend like going for a no driver region because like of the robustness of the results, or should we generate some inflow turbulence for the realistic?
Okay. Yeah. So Okay, so yeah, thank you. So if we don't use the inflow turbulence, firstly, maybe laminar flow, even laminar flow, it is maybe just 1 kilometer. After 1 kilometer, the flow is almost to the fully adjusted to the building geometry. And if we use the inflow turbulence, it's more quickly become more adjusted to the maybe that region, not 1 kilometer, maybe 500 meter or something. Maybe more. Yeah, we can reduce maybe the computational domain. I think it's very efficient. I think.